This lecture is the first one of a sequence of 5 lectures, which have been organized by myself and my colleague and friend Pietro Terna. And the lectures are devoted to the interactions between mathematics, but not mathematics in general, mathematics of living systems, and the modeling of virus pandemics. So it's an important topic because we still, all of us are still under the nefast influence of this world pandemic. This first lecture is devoted to actually to identify a mathematical approach, the strategy to develop a mathematical theory of living systems. Actually, it is very ambitious objective, and we are not so naive to think that we have fully achieved this objective, but simply we wish that some preliminary results will be useful to our aim. So, here is the list of the lectures, and as you can see, it goes from the first lecture, which is the introductory one, up to the modeling and applications to real case studies. Let us define a little more precisely the idea and the objective. So the idea is that we should approach by mathematical tools the modeling and simulation of the pandemics, which, as we know, has affected health, safety, economics, and practically all expression of our collective behavior in our society. But we claim that we should live not from a general mathematics, what is available, but we should look for a new mathematical approach, which accounts for the features of living systems. So we can now start. We need a method. We cannot just start like that. And so in this lecture, we'll point out the method and the strategy, and we'll end up with opening a bridge to the actual mathematical tools, technical tools, which will be presented in the second lecture. It is not a nowadays story, because looking for a mathematics for living systems starts many, many years ago with, it may be, in my opinion, Immanuel Kant, but has seen prestigious contributions from Erwin Schrödinger and several stimulating hints from Hartwell, Nobel laureate like Schrödinger. So where and why and how Immanuel Kant? Well, in the Critique of the Power of Judgment, he has the idea to formalize the way the scientific framework, also in the case of living systems, but he gives a definition which is valid nowadays, and he says very special structures organized and with the ability to chase a purpose. This makes an enormous difference between the inert matter and living systems. Actually, I don't like the idea of the division between hard and soft sciences, although we all are grateful to Auguste Comte, about is the classification of sciences. All of them are sciences, and some of them are soft, while we go to physics and chemistry as the hard sciences. What about mathematics? Definitely is a science. Definitely it is by definition rigorous and cannot really be classified in this framework. But I don't like the idea of classifying. But I wish, before going to the key point, I wish to mention that the great contribution of Erwin Schrödinger is that he is a scientist who effectively explained us that if we want to study living biological systems, multicellular systems, then the problem is multi-scale. Namely, the dynamics of the cells is ruled at a lower scale, while from cells we move to tissues, organs, etc., where organization takes place. Prigogine, another Nobel laureate, has the idea to use methods of statistical physics to model something very, very concrete, very, very precise, the vehicular traffic. And well, cannot be just statistical physics. Something else has to be done, because statistical physics is for particles, for molecules, and definitely entities of the inert matter. Indeed, Lee Hartwell, he gives promotes a research activity just before getting the Nobel Prize. He writes that to physicists, mathematicians, experts in computer sciences, and say, look, biological systems are very different from the physical and chemical systems of the inanimate matter. So living systems need a new approach, a new theoretical approach, and need, in the end, a new mathematics. But I would like also to add Giovanni Iona Lasinio, who explain us that living systems, for instance, populations are an evolutive systems, and evolution can be also brought up to the borders. We don't know whether and how this is possible, but he conjecture that one can move from the inert matter to the living matter by evolution. I don't know. I stop here, otherwise it becomes too difficult for my poor mind. And just to say that the motivation is strong. Is not strong only because of the pandemic. That is an application, is the application that we have selected for our lecture. But we do live in a living world, in a living system. And living systems are also fragile, as we know from our planet, which has been destroyed by the human hands. And so studying the living systems, namely a complex matter, is something that we have to do, also having in mind crisis managers and politics, those who take anyone who takes decision. And we want to build up with these lectures something which is helpful to take decisions within a scientific framework. So just to move from the division from the soft to the hard sciences, I say no, I don't. Already said I don't like it. But I would like to say that I like the idea of a science of living systems. And a science need a theoretical conceptual approach. In the inert matters, we have the physical theories, maybe classical, Newton, relativistic, quantum, maybe one day in the next year a new physical theory will appear, but there is anyway a background theory, a background field which is supporting the derivation of models. What can we do about living systems? My suggestion is a suggestion which is reported in this book. My suggestion is that we should replace the field theory, which we cannot have for living systems, by a mathematical structure, say a mathematical theory, which has the ability to capture all possible complexity features of living systems. Then this structure becomes the framework to derive models. And how models are derived? Well, I will explain actually in this flowchart after having examined the specific system under consideration and studied the scaling problem. We derive a mathematical structure with the aim I mentioned before. I will go back to this soon. Then we learn from Schrödinger that we must model interactions between the entities of the system. We have also to model external actions. Then if we enter with the interactions and external actions into the mathematical structure, then we obtain the model. And then after all is technical, maybe extremely difficult, analytic problems, computational problems, validation of models. And so even, say, pure mathematician will be very happy or very unhappy because analytic problems are extremely difficult. So happy if they solve it, unhappy if they don't. So we move now to the derivation of the structure. Derivation of the structure means a structure with the ability to insert the common features as sources of complexity. Actually, so many. Let us try to select the 5 most important ones. According to all what I have said, I suggest, this is a suggestion, it can be improved, ability to express a strategy. Heterogeneity. Living systems, multi-element living systems luckily are heterogeneous. We are not molecules, and so we have a variety of individuals. Interactions are non-linearly additive. They may involve neighbor entities, but also distant one, depends on the way we communicate. In living entities, learn from past experience and by interactions, and the interactions implement, complement the the past experience. And finally, and this is of all living systems, Darwinian mutations and selection. Actually, in the case of COVID, as we shall see, this is a very important features, but all of them will be present in a way or another. In addition, we have to take care of several things, multi-scale aspects, role of environment, large deviations, and aggregation of living entities, and also birth and death, which may imply evolution and selections. Large deviation play an important role in the validation of models. We will talk about this matter later. And also, I always like the idea of talking about Nassim Taleb, author of the book The Black Swan. And I think that mathematics of living systems should consider also the possibility, the effort to predict what appears non-predictable. But the black swan is something, according to this nice definition, is also something which could be predicted. It was simply difficult to be predicted. Actually, Taleb is very nasty with mathematicians, and mathematicians deserve this kind of criticism. He says that mathematics often or almost always treats only what is predictable. So now all this reasoning will end up with mathematics, mathematical models, applications, or different type of applications to modeling COVID. Actually, I've not mentioned for the moment, I not gave much space to complexity, but this topic will be treated in the fifth lecture by Pietro Terna. So now a little excursus. We are human, and not only mathematicians, and the mathematician can also be a human with feelings, philosophy, and ideas. So I take this the beautiful representation by Esker, the Cornel Exter, is the metamorphosis, and the metamorphosis is evolution. It's, there is, in this case, a passage from a sort of rudimental village made by house with very limited geometry up to a house with rich geometry, a church, which is an expression of some religious idea, and then a bridge and the plate of chess. So, well, this is almost a camp, but we can see. First, let's see that with a little of fantasy, we recognize that this picture expresses several things, such as evolution, heterogeneity, because after everything becomes heterogeneous, and also something very different. So a large deviation to something which has nothing apparently to do with the previous. So First of all, I would like to say that this village exists in reality, is on the Amalfitan coast, is is just before Amalfi, actually. Now is an independent village, but formerly was a part of the more known village or town of Amalfi. Here it is. You can see that it's very much, actually, Cornelis Esker passed 2 years of his life in this area, made a lot of interesting, beautiful, fantastic, especially for a mathematician, pictures. And if you look here, the church is very much like the one we have seen, and then if you do something else, instead of looking the village in this direction, you go from the back of the village, then the tower appears. Complex systems are very difficult to observe, and one has to capture everything. Then the complex system, the tower, the sudden modification of the village and of the geometry. Well, it is something that may be linked to with the period during this period that Europe was entering in an nefast war. So say also the black swan has been represented by Esker, and we mentioned several times that we cannot use what the mathematics which is available. We need a new mathematics, and I just let me say some personal story. Myself, on this terrace, I was a little boy, 3-4 years old. I used to make pictures of this church, because at that time I wanted to become a painter and not a mathematician. Then life changes the destiny of individuals. So I know these places quite well for obvious reasons. Thank you for the attention.